this is part 2 of our logarithmic functions section. We're looking at section 4.2 from the book. We're going to start off with applying basic properties of logarithms. These are, some should be kind of obvious, but I like that I have them listed here with the property and the because. Okay, so log base b of 1 equals 0 is a basic property because b to the 0 always equals 1. So every number to the 0th power equals 1. Log base b of b is going to be equal to 1 because any number to the first power is equal to itself. We have log base b of b to the x equals x because b to the x is equal to b to the x, because you would take the base, put it to the exponent, and then set it equal to this. Okay, so you end up getting b to the x equals b to the x. Okay, so that x has to equal this x. Okay, and then lastly, b to the log base b of x equals x, because if I rewrote that as a logarithm, I would get log base b of x equals log base b of x. Those two x's would have to be equal. Okay, so we're going to simplify each of these expressions using these properties. I'm going to number the properties 1, 2, 3, 4, and I'm going to say which one we're using. On number 20, log base 19 of 19 is going to be equal to 1, and that's using property 2. Number 21, log 10 of 10. Remember, if the base isn't there, we assume that it's 10. That's using property 2, so that's going to equal 1. The natural log of e, remember the base is e, so this is using property 2. That's going to be equal to 1. Log base 273 of 1 is going to be equal to 0. That's using property 1 that I listed up there. Log base 1/8 of 1 is going to be equal to 0 using property 1. Log base 30 of 30 to the 10th is going to be equal to 10. That's property 3. Okay. The natural log of e to the negative 12th is going to equal negative 12. Okay. And that's going to be property 3. 10 to the log of 14 is going to be equal to 14, and that's based on property 4. And 8 to the log base 8 of 5 is going to be equal to 5, and that's for property 4, from property 4. These basic properties show up a lot, and it's really important to know them and have them down. So make sure that you write these down and have them handy, especially when you're doing your homework. I'm also going to say that the homework for this section, there's a lot of questions. There's like 23 questions on it, but many of them are quick ones like this and like this and like this. Okay, so there's a lot of questions, but they should go quick. So if you have these properties and you know them, you should be fine. Okay, so the next thing that we're going to do is we're going to look at graphs of logarithmic functions. And I wrote a little hint up here. My hint is we're going to rewrite this in exponential form and then select values for y first. Okay, so I'm going to rewrite this. The base is 3. So I'm going to say 3 to the y equals x. And I'm going to select some values for y. I'm going to select my favorite 0, 1, 2, 3, negative 1, negative 2. Okay, I have more spaces than I'm actually going to use. And then I'm going to substitute in those values for y and solve what I get for x. So 3 to the 0 power is equal to 1. 3 to the first power is equal to 3. 3 to the second power is equal to 9. 3 to the third power is going to be equal to 27. 3 to the negative first power is going to be 1 over 3. And 3 to the negative second power is going to be 1 over 3 squared, which is 1 over 9. So I have all of those points. Okay, I'm going to draw a quick graph here. We're going to make the scale on this graph by 1. So when x is 1, y is 0. That's that first point. When x is 3, y is 1. When x is 9, so 1, 2, 3, 4, 5, 6, 7, 8, 9, we get 2. This one is off the graph, OTG. So I can't plot that one on here. These next two are going to be very difficult to graph or plot because they're so tiny. I'm going to do my best. When x is 1/3, we get a -1. And then when x is 1/9, which is even smaller, we get a -2. So I hope you, so difficult. Okay, so I'm going to connect those here. So this is my logarithmic function. Okay, now one thing I want to point out, and this will get you on your homework, they're going to ask for you to draw in the asymptote as a dotted line. So these functions, these logarithmic functions, have an asymptote, a vertical asymptote, at x equals 0 unless they are shifted. Okay, if they're shifted, it could be moved over left or right. All right, but they have an asymptote, a vertical asymptote. Okay, your homework is going to require that you graph it, and it will count it wrong if you graph the function without the asymptote. So please make sure that you include that. Now remember, exponential functions had a horizontal asymptote at y equals 0, unless it was shifted up or down. So these are inverse functions. So it should make sense if this is a reflection over that line y equals x, that if I had a horizontal asymptote on an exponential function, then I should have a vertical asymptote on a logarithmic function. For this next example, we're asked to graph y equals log base 2 of x plus 1 plus 2. Now, this is a transformation of the graph y equals log base 2 of x. So our first suggestion is going to be rewrite this function y equals log base 2 of x as an exponential function. Select values of y, solve for the values of x, okay? Then we're going to take that, graph it, and then we're going to shift it. So this shift, we're going to have a left by 1 from this right here, and then we're going to have an upshift by 2 because of the adding of 2. So I'm going to plot the original function y equals log base 2 of x on our graph. I graphed that function in orange. And now for the final function, I'm going to take each of those points and I'm going to shift them left by 1 and up by 2. So this point at 1, 0 is going to move over left by 1 and up by 2. Okay, this one, left 1, up 2. Left 1, up 2. Left 1, up 2. So use what we know about our transformations to get the points that we need. And save yourself the hassle from doing all of these computations. Don't do those computations. Do the computations for one that we know and then shift it. Okay? So the final graph, I'm going to graph in blue. That is our shifted logarithmic graph. And because we had a left shift, our vertical asymptote shifts left by 1. So in this case, my vertical asymptote is going to be x equals -1. We can also think about what's our domain. What's our domain on this function? Our domain, or our x values, start at -1 without touching -1. So we're going to put that in parentheses. And it goes forever to positive infinity. Our range, okay, is going to be from -infinity to infinity. Now recall from section 2.7 on inverse functions. If I have a function that's exponential, its domain is -infinity to infinity. If a logarithmic function is its inverse, then its range would be equal to the domain of the exponential. So you should see that our range here should be the same as the domain of an exponential function. I wanted to include this chart really briefly. Again, this is just a recall of all of our transformations that we might see, vertical and horizontal translations. We could have reflections, we could have vertical stretch or shrinking or horizontal stretch or shrinking. And these are just examples of what they would look like when we're dealing with logs, okay? So please, please, please take note of this, take a picture, screenshot, whatever you need to do. But make sure you have these shifts and stretches and reflections down. And then the last thing we're going to look at for logarithmic functions is their applications. Now, logarithmic functions have a lot of applications. Our Richter scale is an example of a logarithmic relationship. So when they determine the strength of earthquakes, they're using that scale. And in this example, we have the magnitude of stars. So this question states, the absolute magnitude m of a star is the apparent magnitude, lowercase m, a star would have if it were placed 10 parsecs from Earth. The lower the value of the magnitude, the brighter the sun. Our sun has an apparent magnitude of negative 26.74. The brightest star in our night sky is Sirius, the dog star, with an apparent magnitude of negative 1.44. The sun appears so bright because it is so very close, astronomically speaking. The formula, absolute magnitude equals the apparent magnitude minus 5 log of d over 10, where d is the distance and m is, lowercase m is the apparent magnitude, relates these three relationships in order to find that absolute magnitude. So they tell us if Sirius is 2.637 parsecs from the Earth and the sun is 4.887 times 10 to the negative 6, so that's some nice scientific notation for us right there. Parsecs from the Earth, what is the absolute magnitude for each star? So the cool news about this is we just have to be able to calculate it, and they provide the formula for us. So we don't have to derive anything too difficult. We're just trying to find the magnitude, the absolute magnitude for Sirius, and the absolute magnitude for our sun. So we're just going to substitute in the values, then very, very carefully and put it into our scientific calculators and get the result. So for Sirius, it's going to be negative 1.44 minus 5 log. And remember, log is going to be base 10. It's assumed because they didn't write it out. Okay, and for the sun, it's going to be negative 26.74 minus 5 log of 4.887 times 10 to the negative 6 over 10. Okay, and we get the following results. So Sirius has an absolute magnitude of 1.45 if I round to the nearest hundredths place. And the sun has a absolute magnitude of 4.81. Now remember, it says the lower the value of the magnitude, the brighter the star. So which one would be the brighter star? Okay, let me know if you have any questions about this. Please work on your 4.2 homework and email me if you have any questions. Thank you.